Okay, I think we can start this next talk of this session. So the next one is an invited talk by Professor Amit Tandon. I try to say that. So he's from the University of Dartmouth in Massachusetts in USA. And he will talk about oceanic sub-mesocale instabilities and the manifestation in the Bay of Bengal. And we look forward for your talk.
Thank you, Sylvain. I would first like to thank the organizers of this meeting for inviting me. I'm very pleased to be here. In talking to the organizers, they mentioned to keep the talk pedagogical, so that's the level the talk will be at. The work that I'll be presenting is not just mine alone. It involves many other collaborators from some long-term collaborations that have been going on between India and the US. And these were the air-sea interactions initiatives funded by ONR in the US, Assyrian Mesobob, and the ocean mixing and monsoons initiative funded by the Ministry of Earth Sciences in India under the Indian Monsoon Mission. So I really hope that we can meet in person in ICTS. Although this works fine in terms of delivering the talk, I think I'm missing the flavor of ICTS cafeteria food and the ability to discuss with my colleagues more closely. And most importantly, all of us being in the same time zone, so we can have free discussions with each other. And then the ability to swim in the ICTS swimming pool in April would be fantastic. So I hope we can all meet in person in the next year or two. So what is the sub-mesocale? I wanted to show you a picture first to give you a sense. This is a picture that was published in the New York Times. And this is a picture of the Arabian Sea, as you see in 2014. So what you're seeing on the top end are parts of Pakistan, and on the west of that, Iran. And what you're really looking at is sea surface chlorophyll. And the scale down below is showing you 0 to 200 miles and 0 to 200 kilometers and 200 to 400 kilometers. So roughly the screen width here for the picture is approximately, I would say, about 500 kilometers. So there you see some eddies, some mesoscale eddies, which are order, a couple of 100 kilometers in the Arabian Sea. But then you also see lots of filaments, and there are there are instabilities at the edge of the eddies where you can see them spiraling out. You see the chlorophyll being drawn out in filaments. It could be drawn out laterally, but it could also be fed by the nutrients vertically. So there is a lot going on there. There are both lateral motions and vertical motions going on. And there are important questions related to images like these, which is in terms of how does the carbon get sequestered in the ocean, and over what time scales, and how much of it is permanently gone versus how much of it can sort of come back to the atmosphere by air-sea exchange. So there are very important implications of a class of motions which are less than mesoscale. So here is another example. Again, this is off of Gujarat coast. So this would be very familiar to my colleagues who are attending from India. This is a typical eastern upwelling boundary system in the northern hemisphere. So the cyclonic rate of rotation of the Earth is going to be anti-clockwise. This is a slide from my colleague Amala Mahadevan at Woods Hole. So what we see here are winds coming from the north, and as they come from the north, there is, of course, Ekman transport to the right of the wind. So that brings up this cold, nutrient-rich water from below, and basically has a surface jet which is in geostrophic balance with cold water towards the coast and lighter, warmer water towards away from the coast. And what happens is that this doesn't just come up in a uniform jet, but that jet, as you can see, breaks up, and it breaks up into eddies and filaments that you're looking at in the chlorophyll image again. This is from the ocean color monitor instrument off of Gujarat coast. And these filaments transport dense water offshore, leading to important cross-shelf transport. So if you're interested in cross-shelf transport of nutrients and many other tracers like that, then this kind of system is very important again for upwelling systems. Another reason why we really care about submesoscales is because if you're familiar with the geophysical fluid dynamics, you would have heard that the energy cascade is inverse at the larger scales in the ocean. So the mesoscales are fairly non-dissipative. They are essentially two-dimensional. The Rossby number is much less than 1, which means that they are fairly linear. The Richardson number is much larger than 1, so their motion is very much dominated by strong stratification. The length scales are fairly large, order 100 kilometers. We just saw a few 200-kilometer eddies in the Arabian Sea. And again, I have Arabian Sea picture in the background showing fronts and filaments. The aspect ratio is such that, you know, the depth ranges we are talking about is typically hundreds of meters for mesoscale eddies, maybe a kilometer, but the length scales may be 100 to 200 kilometers, particularly in the Bay of Bengal. So we are essentially talking about hydrostatic dynamics. So these scales are not particularly dissipative, but we know that if we go out and measure mixing in the ocean, there is dissipation going on, certainly in the boundary layers, but and weaker in the interior, but there's certainly forward cascade of energy at the small scales. And at those scales, the Rossby number is much larger than 1. So we are really in you know, the fluid dynamics regime in the sense of traditional fluid dynamics, like flow over cars and things. So nonlinearity is very important. The length scales are you know, much less than 100 meters. Typically, we are thinking of Thorpe scales of, you know, order 10 meters or so. And then the aspect ratio is order 1. So the fluid flow is certainly non-hydrostatic. And the rotational constraints that arise because of the Earth's rotation are much weaker. So the question is, we know that there is energy dissipation at the smallest scale, but at the QG level, in theory, the cascade is inverse. So how does energy get in from these large scales to the dissipative scales? And so a lot of that, I'll just give you the answer now. A lot of that happens at the submesoscales, and it happens at fronts and filaments, and it happens by frontogenesis. And these eddies, at the edges of these eddies, as they begin to squeeze the water in through frontogenesis, that's where a lot of dissipation actually takes place and takes it to the forward cascade. So let's talk more now about what oceanic submesoscales are. So I'll start out with a very general introduction by looking at the scales of motion in the ocean and how do we think about them. And we will think about them in terms of a conserved variable, as you've seen in other talks, whether it was, you know, astrofluid dynamics or something else. So today we are going to talk about them in terms of a quantity called the potential vorticity. And a potential vorticity is nothing but essentially a combination of the absolute vorticity and buoyancy gradient. So we'll define that. And we'll think about this conserved variable at various different scales. So the scales we choose spatially and temporally are important. And that will bring us down to what we really mean by submesoscale in the space-time, you know, in terms of a chosen spatial scale and a chosen time scale. We will think about what really generates these submesoscales. So again, as some of my pictures have shown, we'll quickly come down to fronts and filaments and eddies. And then I'll talk about how these may get generated both by unforced motions in terms of what are called mixed layer eddies. These are upper ocean shallow phenomena. as well as instabilities, which you may have heard of or know very well from other contexts, symmetric instabilities. We will also talk about what difference does it make to have forced motions in terms of both wind forcing and buoyancy forcing at the top. So you may be, losing heat or forcing the ocean by different kinds of wind forcing. And then you may be familiar with the linear Ekman solution, which was almost derived now 120 years ago by Ekman as a graduate student. So we'll talk about what happens when you bring in nonlinearities. And last but not the least, I'd like to spend some time discussing a few examples of the Bay of Bengal that relates to all the theory that we've discussed. So, okay, so what's PV? So if we don't have friction, if we ignore friction, and if we ignore any kind of diabatic processes, heat exchange and so on, for a rotating Earth and a density stratified fluid, the quantity that's conserved is potential vorticity. So potential vorticity, we can think of it as a dynamical tracer. So think of PV as 1 over rho times absolute vorticity dotted by grad rho or grad B. And then in the context of the Earth, if we ignore, if we are far away from the equator, then we can ignore the horizontal part of Coriolis. So what we are left with is the vertical vorticity, which I'm going to write as F plus zeta in the K direction. And that's dotted up with grad HB, which is the horizontal buoyancy gradient, plus the stratification again in the vertical direction. So in the first bracket, when you have F plus zeta, think of zeta over F as a measure of the Rossby number, because that's, think of that as the ratio of nonlinear terms to the Coriolis term in the equations of motion. I'm not showing you the full equations of motion, but I think this is just kind of a quick review of what you may have learned in the GFD. If you haven't, then send me an email and I'll send you some references or some books that you can quickly pick up. For starters, I really like the book by Cushman-Rosan or the book by Jim McWilliams. So, and then a second non-dimensional number we'll think about. It tells us how layered the ocean is, what is the stratification, and the competition of shear squared. So think of that as a competition between the shear squared trying to make the ocean unstable and the stratification having a stabilizing influence. So the Rossby number is really a measure of nonlinearity in this sense compared to the influence of Earth's rotation. And the Richardson number really an influence of the stabilizing effect of stratification against the shear. So at the larger scales, if you're thinking of basin scales, really the Earth scales, L, the length scale of the order of 10,000 kilometers, and the H for the entire ocean depth, about 5 kilometers. Then at that scales, the force balance is essentially between Coriolis and the pressure gradient. So we can think of the potential vorticity as just Fn squared. And so, the isopycnals have near zero slope. The buoyancy surfaces are pretty much flat. Very low Rossby number. The dynamics is linear. And if you pick up a book by Wallace, for example, or some of his papers, he's considered these PG equations of motion to think about how the thermocline gets set up at the larger scales, at the basin scales. Next, we go down in scale and say, oh, but the PG is, really for the larger scales. What we are really interested in, what happens at somewhat smaller scales. And as you go to oceanic mesoscale, the eddies begin to arise from baroclinic instability of the main thermocline. So here, what we are really thinking about is the height of the depth of the main thermocline, which is order 1 to 2 kilometers. And then the horizontal length scales, which begin to become important, are given by the Rossby radius of deformation, sort of NH over F, which are 100 kilometers in mid-latitudes or so. And now, if we think of the potential vorticity of the mesoscale eddies, we can take the next term that was there in my PV equation. So that's F plus zeta n squared. So typically zeta over F will be order, plus to minus 0.2. So you will have both cyclonic and anti-cyclonic eddies. These can be seen by remote sensing very clearly. For these kinds of mesoscale eddies, the density surfaces still have small slopes. So we are still in the regime of where the Rossby number is much less than 1 and Richardson number is much greater than 1 in terms of the two parameters that I talked about. So the dynamics is still fairly linear. And in this case, the vorticity dominated regions, which are cyclonic or anti-cyclonic eddies, are quite separate from the strain dominated regions. So you can think of mesoscale eddies as essentially containing the vorticity, and then in between them are regions which are dominated by strain, which are being strained by the mesoscale eddies. And there are criteria like the Ukubo criteria, which can really separate these out. What happens as we start going to next smaller scales is very interesting, because if we think about what happens when we go down in scales next, then in presence of density gradients, which can now come in near fronts or filaments, the isopycnals are no longer flat. They can now come up and outcrop near the surface of the ocean. So the density slopes are no longer small, so you can't do the same kinds of expansions that you could do for mesoscale dynamics or the QG dynamics, the quasi-geostrophic dynamics. So now you have to think about, okay, what happens next if I do have to take into account the horizontal buoyancy gradient that becomes important. So we can still think of, for example, a perfectly linear front, which is in geostrophic balance. So now we have tilted isopycnal surfaces, and the velocity shear in the perpendicular direction balances the horizontal buoyancy gradient. And in this case, we can define the potential vorticity. I'm just dividing by Fn squared to still keep it in terms of Rossby numbers and Richardson numbers. So if we have a perfectly balanced geostrophic linear front, then this quantity, the scaled PV, is 1 plus Rossby number minus 1 over Richardson number. So if if in the limit of Rossby number small and Richardson number large, you still get back the same kinds of dynamics. But in this case, the horizontal term can significantly contribute to the total PV when Richardson number is order 1. And so that can begin to reduce the PV. And as the PV goes to 0, we are going to have classes of instabilities coming in. The two things that you can see from this expression right away that I have put in pink. One is that if the Rossby number goes to -1, even irrespective of what's happening baroclinically, in strong anticyclones, if the Rossby number goes to -1, then that can give rise to barotropic instabilities. And of course, once you combine it with baroclinic term, which is all contained in the third term, then that gives rise to even more interesting dynamics. So the horizontal term can reduce the PV, the anticyclonic term can reduce the PV. If PV is equal to 0, then the flow becomes non-invertible and it becomes unstable. And so sub-mesoscale dynamics in the ocean are intimately linked with processes that can modify the potential vorticity. The other things that can modify the potential vorticity are wind stress and buoyancy fluxes, because you can put in PV, you can take out PV at the surface, and you can advect PV by the eddies themselves. So let me keep defining what interesting dynamics happens at these scales. So both observations and simulations have now shown that there are filaments and structures at order 1 to 10 kilometer scales. These structures typically have order 1 Rossby number, order 1 Richardson number. They can generate large vertical velocities, while still the deviations from thermal wind balance are small, but they break the constraint of the QG mesoscale velocity being really small. If you look at the scaled equations of motion for the QG under the QG approximation, then the vertical velocities turn out to be really tiny. They are order Rossby number squared. But as Rossby number becomes 1, you can no longer ignore them. So at sub-mesoscales is where the ocean's vertical exchange becomes really dominant. And so if you think of this in terms of our breathing planet, then fronts and filaments, oceanic fronts and filaments is where most of the vertical exchange is going on. That's where most of the carbon dioxide and oxygen exchange, air-sea gas exchange is also going on in terms of the interior ocean being sort of the lungs of the earth, and the and these are the alveoli by which you do most of the transfer. So in terms of coming back to the dynamics, these play an important role in fluxing the energy downscale and loss of balance. And I already told you how that happens in terms of frontogenesis. These motions also play a role in terms of spreading tracers vertically from surface to the interior, and they also change the stratification of the mixed layer. Towards the end of my talk, I will also show that recent studies show that flow curvature also matters. And this is work done by both Christian Buckingham and some very interesting work done by Suraj Singh and Manikandan Mathur. Although I will not talk about that, I hope Mani or Suraj will talk about that to you at some point. So sub-mesoscale processes are very different from the QG mesoscale processes. They're also very distinct from the internal gravity waves that you heard in the previous talk about. They're particularly dominant in the upper ocean because of lateral buoyancy gradients. They have an associated surface frontogenesis. They're associated with weak stratification in the mixed layer. So again, we are breaking the constraint of strong stratification at these scales, and they typically have smaller Rossby radii. The Berger numbers are still order 1. The Rossby numbers are order 1. They can still be largely hydrostatic though. And these processes, as I will show you in the rest of the talk, lead to a zoo of instabilities. So they are mixed layer instabilities, which are more like baroclinic instability, but at a different scale. Symmetric instabilities, force symmetric instabilities, a hybrid of these instabilities. And there are also other animals in the zoo like the anti-cyclonic, ageostrophic instability, and so on. So let's look at some pictures now and think about how they arise. So one picture that I'm showing here on the left is from a paper by Amala Mahadevan and myself, where what we did was we took a front, a perfectly linear geostrophic front, and then we blew some wind on it at the surface. And one section of this is shown in terms of density. So the density is heavier, where you see red pictures on the top, lighter on the south side. And you see these, again, these strong filaments in density, but they are associated with strong frontogenesis. If you look at the UV at the surface plot, which is the top row, third plot from the right, you can see very strong frontogenesis happening in the surface. And along with that, what is shown on the top panel, fourth panel on the right, is an overturning circulation, which is happening along a section, showing you that there is sort of sharp downwelling regions close to the surface that extend almost to 250 meters here. Our mixed layer depth, I think, was something like 150 meters, and then broad upwelling regions on the lighter side of the front. The Rossby numbers are certainly, order 1, much bigger than 1. The strain regions are again order 1. And interestingly here, the strain regions and the high Rossby regions are not separated. They can occur side by side or even overlap. The gradient Richardson numbers are certainly order 1 here. And so in this case, this is just weak winds. And there are cartoons in the literature. One I'm showing you from a chapter by Jonathan Gula here, which shows that if you just think about this in terms of a single front, then there's an ageostrophic secondary circulation that gets developed by the large scale strain. So what's providing the large scale strain? The large scale strain can be provided by the frontal instabilities themselves, or even by the mesoscale eddies squeezing the isopycnals together. You can also have, so on the left in the cartoon sketch is a single front, on the right is what happens if you put two fronts side by side, and that leads to even a stronger ageostrophic circulation, very strong downwelling for a dense filament. We can so what can generate submesoscales? Well, there is one set of generation mechanisms that consists of unforced instabilities. So if you just think of a storm that mixes the ocean and then leaves a dense water on one side of the ocean and lighter water on the other, then now you've created a front, and as the storm leaves, it leaves behind this front which is no longer in balance. So this front will now undergo inertial oscillations. It will tilt, and as it tilts, it generates these. It goes unstable. Further unstable generates these mesoscale eddies, which are shown on the left from a paper by Fox-Kemper, on the right in a review paper that we wrote in 2008. And so what you get are this front generates these submesoscale eddies. And these submesoscale eddies are essentially being generated by baroclinic instability, except that this is not a small Rossby number baroclinic instability, but this is order 1 Rossby number baroclinic instability. And this was analytically done by Peter Stone in 66 and early 70s set of papers. So this is an ageostrophic baroclinic instability. And since this happens close to the surface of the ocean, we call it mixed-layered instability. So here the depth scales are determined by the depth of the mixed layer. The horizontal buoyancy scales are determined by the frontal buoyancies near the surface of the ocean. It turns out that this ageostrophic instability can also occur in the bottom boundary layer, and I'm not going to talk about that, but that's you can also think about, again, the same mechanism, but in the ageostrophic case. So let me show a little movie just to tell you what, just to show you what these instabilities look like. On the left-hand side in the density, and on the right-hand side, I'm showing you both the density fields as well as the stratification. So you can see that when we started out, the water wasn't well stratified, but one major impact that these instabilities have is they release the available potential energy. So they convert this horizontal buoyancy into a strong vertical buoyancy gradient. And so the restratifying effect of the mixed layer eddies is because of releasing the available potential energy by this mixed layer instability and by self-induced frontogenetic effects. Of course, in this case, because it was unforced, you could see the inverse cascade as the eddies become larger and larger as the time goes on. But most of so there is definitely an inverse energy cascade going on because these eddies are getting larger with time. But there's also a forward cascade at the edges of these eddies in terms of what is happening at the fronts. So there's been work saying, how do we parameterize them? Because we do want models of climate which are not going to resolve this kind of phenomena in terms of this added stratification. And it turns out that this can be done by an analogy with previous work, and this can be done in terms of thinking of what the eddies are doing is an overturning stream function. And this overturning stream function is proportional to the mixed layer depth squared. It's proportional to how strong the fronts are, and divided by the Coriolis parameter, and a mu of z function, which is a near quadratic function in the surface mixed layer. So what happens? So these were unforced motions. What happens if we now add forcing to it? And if we add forcing to it, then we can generate again these submesoscale motions by either differential cooling, as was done by Tom Hayne and John Marshall back in 1998, although they didn't call them MLIs. These eddies of the order of 1 to 10 kilometers, what they saw were the mixed layer eddies. And you can have a mesoscale eddy field as shown in the lower plot, and if you put surface cooling on top of that, you can again generate submesoscale baroclinic instabilities very similar to the mechanisms we had before. So the mixed layer instabilities and the forcing can coexist. They can exist side by side. They can compete with each other. Here is another figure from our paper with Amala, where we showed that we can, as I said earlier, it's the vertical exchange that these generate, because that vertical exchange basically breaks the quasi-geostrophic constraints. So in a forced case, we can think of the Ekman Ekman flux as mass transport flux is not just tau over rho f, but we can think of it as tau over rho f plus zeta. So now that's being the vorticity that matters is the local f plus zeta vorticity, and you can take the derivative and think of that in terms of what does vertical exchange then, what vertical exchange does it imply? So it implies a vertical exchange not just because of curl tau, which is the first term in this Ekman term, but also because of the variation of the vertical vorticity. So, d zeta dn, partial zeta partial n in this case. And so that we call it a nonlinear Ekman transport, a nonlinear Ekman vertical velocity, because now we have to take into account that the vorticity is varying on smaller scales, not just on large beta scales, but at smaller scales at the order of 1 to 50 kilometers. So another instability that arises when you're thinking of order 1 Rossby number and order 1 Richardson number is symmetric instability. So again, without showing you the equations, I'm just saying that strong buoyancy gradients can lead to density surfaces. And if the density surfaces have slopes which are near vertical, and they have a stronger slope, higher slope than the absolute momentum surfaces, then essentially fluid parcels can slide and until and grow into an instability which is which does not vary in the other direction. So that's why it's called symmetric, because there is no variation along the front, but it leads to, people often describe it as slantwise convection. So it's not convection in the generic sense, but there's certainly slantwise motions. And so for that, the PV has to be less than 0, but as we know that in the interior, we cannot create or destroy PV. So how does that happen? And so one of the works by John Taylor and Ralph Ferrari early on showed that you can have, you could be taking PV out, for example, by cooling at the surface. So that gives rise to one layer, which is a convective layer. And then below the convective layer, there is slantwise convection going on. So even though you might see positive n squared or positive stratification in these regions, it's not as if they're just stable, but there is slantwise convection going on. And the way the PV is being reset is by mixing the low PV water, which is being created by the suction of PV from above, but by mixing it with the high PV water from the interior. And and that happens by having Kelvin-Helmholtz instability at the smaller scales. So clearly, if we are going to resolve both symmetric instability and Kelvin-Helmholtz instability, then we have to go down to large eddy simulations of the kind that are shown here. There are multiple things that occur when you have fronts and stratification and vorticity. So this was investigated by Leif Thomas in a very interesting deep sea research paper where they were looking at the competition between symmetric instability and baroclinic instability in the context of the Gulf Stream. So this leads to just like we can think about these instabilities for double diffusion, here we are going to be in a parameter space where we're going to think about whether the vorticity is cyclonic or anti-cyclonic in terms of the eddies themselves. On the x-axis is f squared n squared, so you can think of as a measure of stratification. And on the y-axis is the frontal strength, so grad b squared. So let's just look at the anti-cyclonic vorticity diagram for a moment. So when we are in case where the horizontal buoyancy gradients are weak, and n squared is positive, then the situation is stable, as you might expect. But then as the buoyancy gradients get stronger and stronger, we get into a combination of inertial and symmetric instability, where the source of instability is coming from the lateral shear. As we go further in terms of as the buoyancy gradients become stronger, as the fronts get even stronger, then we are going into symmetric instability, where now the main source of where the energy is coming from is the geostrophic shear production. Of course, if we are talking about n squared negative, then there's going to be gravitational instability. And depending on whether the source is the buoyancy flux or the geostrophic shear production, we'll call it a symmetric gravitational instability or gravitational instability. So these kinds of diagrams are very important in telling us what's going on in the ocean. We can do this for cyclonic vorticity as well. And again, n squared less than 0, you still have the two classes of combination of gravitational and symmetric instabilities, depending on what the source of energy is. On the right-hand side term, you can see that there's a larger part of parameter space, which is now stable. But even with cyclonic vorticity, we can have symmetric instability where the source of energy is the geostrophic shear production. Okay, so let me stop here now and let me give you a sort of a cartoon view of what's happening in the ocean. So as we said, down front winds can generate eddies. Even in absence of any forcing, you can have mixed layer instability, which is being shown by MLI. And these eddies themselves have a sub-mesocale strain field associated with them that can dissipate energy and take it to the forward cascade. At the larger scale, there are mesoscale strains that are squeezing these fronts together. There's ageostrophic secondary circulation that's going on close to the fronts. One aspect that I didn't talk about was the friction within the boundary layer can give rise to a modification of the thermal wind, which is now called turbulent thermal wind balance, or TTW. And there is subduction happening on the dense side of the front in combination with the boundary layer turbulence. So there's very, very interesting vertical dynamics going on at the edges of these fronts and filaments. I want to now...
Sorry, there is a question on the chat.
Yes, please go ahead.
The question is by Yohei Onuki. Where does the ageostrophic baroclinic instability belong in the Thomas angle?
Oh, it doesn't, because the Thomas angle is essentially talking about scales much smaller than what we're talking about. So for symmetric instability, remember, we have to go down to smaller scales. The ageostrophic baroclinic instability comes in where essentially the scales are allowing for a long stream variation. So this Thomas angle, strictly speaking, has no along stream or along frontal variation. That's a very interesting question, because in many of our simulations, we've seen that if we begin to do the simulations in a range, which can certainly resolve the ageostrophic baroclinic instability, but begins to resolve symmetric instabilities as well, meaning partially resolve symmetric instability, then you get these hybrid instability modes, which are both baroclinically unstable, but also have some features of the symmetric instability. So there's at least two sets of simulations, some done by my group and some done by Baylor-Fox-Kemper's group, where we can begin to see these hybrid modes. And so I did not include them here, but I can certainly talk to you later about them. One of Baylor's students has done important work in that. So I wanted to talk about the Bay of Bengal examples, and here is an example from Srilekha's thesis. I think this is being prepared as a paper by Srilekha, Debasis, myself, and others. So what I'm showing here on the left is a salinity section, and this is from one of the cruises on the Sagar Nidhi in the Bay of Bengal. What I want to draw your attention to, and so in the Bay of Bengal, these fronts are very strong in salinity. The buoyancy gradients are like 10 to the minus 6 per second squared in the horizontal. And but the fronts are not as deep as we see in their mid-latitude cousins. So the mid-latitude cousins are like order 100 to 150 meters deep. Here in the bay, the shallow cousins are order 20 meters deep. So what you're seeing here is very sharp front on the left. And then as you go further to the east, you see the density surfaces shoaling. And there is a more complete 3D section in the middle panel, which is again showing very salty water to the west and fresher water to the right. And this relatively fresher water is, we know it is essentially river water being stirred by the eddies. But the question here is, why do we see this very strong asymmetry in the front? Why is it so sharp on the west side and then, you know, shallowing to this on the right-hand side? So imagine that you have a river water which is in the middle, you know, which is being squeezed by these two mesoscale eddies. And now remember that for summer monsoon, the winds are from the southwest to the northeast. So the winds are such that you can see in the cartoon on the right, the winds are such that they are essentially going from southwest to the northeast. And the orientation of the front is shown here. So even if we started with a perfectly symmetric front, what would happen over time is this Ekman effect will try to send heavier water over light on the western side, and it would give rise to deeper mixed layers and convective, you know, essentially heavier water mixing with the light and give rise to deep MLDs. Whereas on the right-hand side or on the eastern side, the wind forcing will force an Ekman current, which will kind of spread lighter water over the heavier water, thus leading to this asymmetry. So you're going to have sloping isopycnals on the right-hand side, you know, being squeezed into thinner and thinner mixed layers until they get well mixed, and that'll lead to some limit on the eastern side, whereas on the western side you'll get these deep mixed layers. And so it's fascinating to go out on a ship and make these measurements and really see the ocean behaving as you think it should be behaving under downfront wind conditions, which often happen in the Bay of Bengal under these. So for more details, you know, Srilekha's thesis or this paper being prepared. Another example I would give, and this has been published, so this is more easily accessible. This is a case in which we were out in the winter monsoon 2013, and this is on Roger Revel. So where you see the central box, we did a radiator pattern with Revel. So these sections AA, BB, CC, etc. And so again, we have you know, heavier fluid on the south side and lighter fluid on the north side in general. We also deployed a wire walker in there, so that gives us some idea of the stratification as well. In the inset is being shown the Aquarius salinity in terms of black lines. So there's a strong salinity gradient there, which is what is giving rise to the density gradient, horizontal density gradients. And what is being shown in color is the sea surface height. So that gives you a sense of the mesoscale field. So this was at the edge of a mesoscale eddy in a confluence region. What is shown on the right-hand side is that the winds were fairly weak, but even though the winds were weak, they were mostly in the downfront sense, because you can see for one of the days, the bottom panel shows the net heat flux. So where it goes negative, that means that the ocean is gaining heat. But there is an Ekman heat flux, which is for section C and D, particularly in the opposite sense. So the winds are trying to create an Ekman heat flux, which is mainly countering or more than countering the solar heating during this time. So we did we did sections with the underway CTDs at 0.7 to 1 kilometers, and each transect is 4 to 6 hours. The overall flow is going towards the west-northwest, but there is a sense of squeezing that you can see even in the sections themselves. So what happens there? What we see there are very interesting features. Certainly we see strong fronts. You can see here a light filament with fronts on either side of it. There are pycnostats that arise. So there are features where the density is more or less constant. And near the surface, the density is primarily governed by ds/dz, or the salinity. And then below about 50 meters, it's primarily governed by the temperature. So these fronts and pycnostats, how do they arise, and are there instabilities going on in the Bay of Bengal during this time? So we have many ADCPs on the ship. Some of them that are very high frequency, so we can actually map out the vorticity at different smoothing scales, and we've smoothed out the ADCP to find the vorticity. But the main thing I wanted to show you is that even after we smooth it out to 8 kilometers, there is still both anticyclonic and cyclonic vorticity, which is order 1. And so then we can apply the Thomas conditions and ask, are the conditions for symmetric instability satisfied? And indeed, there are many places in which they are satisfied. In some places because of the anticyclonic vorticity, in other places because of very strong horizontal buoyancy gradients. So going back to the Thomas angle, we can figure out what is the source of these instabilities. So just to give you a summary of, here is a salinity filament, and then in black are shown the density lines. So what the picture we have are that the winds are blowing, they're creating downfront conditions, they are taking vorticity out. Both cooling and winds are reducing the PV in this region. This PV then gets subducted by frontogenesis. And as it gets subducted, since PV has to be conserved, it goes from a baroclinically unstable, mostly baroclinic PV to, as it goes down, since this low PV has to be conserved, as it loses the baroclinicity, it has to lose it has to generate more anticyclonic vorticity, and it has to stay close to 0 PV. And so that's what generates the pycnostat. So creation of 0 PV by force symmetric instability and inertial instability, and that leads to these low PV waters. Then, that's what gives rise to these pycnostats that we were looking at. And so then we did some numerical simulations that showed that if we blow some weak downfront wind and then stop the wind, what happens is that these low PV regions get created, then they get subducted. And these have a length scale in the horizontal of order tens of kilometers. And in the vertical, these are order 20 meters thick. And so the other interesting thing that happens with these regions, getting away from dynamics now, but looking at now temperature, is that you can get warm water and you can subduct it below this stratified layer, as you're seeing in panel A, B, and C on the right-hand side. And then these basically volumes of water, which are tens of kilometers long and maybe 10 to 20 meters thick, are basically heat sources that you've shielded and then created barrier layers in the process. And so what can happen now is that if you have a subsequent storm or a cyclone, then these sources of heat are essentially sitting shielded, a few tens of meters below the surface. So if a severe weather system passes by and it can mix if it can penetrate through this near surface stratification, then now suddenly you have a big source of heat that can come from the ocean and really energize these systems. If you were doing a prediction system which did not take into account these subsurface boluses of heat, then you would miss out on this source of strengthening. And we think these are in part, so firstly, it's not just 1D mechanisms that gives rise to these kinds of barrier layers in the Bay of Bengal and other places. And secondly, these can be an important source of heat for severe weather events, and they can lead to intensification of storms, monsoon storms, and others. So here is my last example, and this is by Taylor McKee, Jen McKinnon, and Andrew Lucas. This was presented in the Ocean Sciences Meeting 2022. And this is based on a cruise in the Bay of Bengal in 2019. And what we are showing are, again, some transects. What is shown in the background are the sea surface heights. So you can see there's a mesoscale eddy, and again, transect A and B are sort of in this frontogenetic region. What is shown on the right is just one of the transects here. And I don't want to say too much except say that, again, Taylor McKee is doing this analysis. And she shows very convincingly that essentially there's a region here where the flow gets subducted underneath. So if you look at the salinity again, on the east side is this relatively fresh layer. In this case, now you have a strong salinity front. But in between here, if you look at the dt-dz plot, you can see that there is water that gets subducted, and these are at the gateway of the at the mouth of this subduction region is where she sees multiple symmetric instability signatures going on, both in terms of anti-cyclonic geostrophic shear production and lateral shear production, and strong anti-cyclonic vorticity being created at these mouth regions, leading to creation of barrier layers. One last topic that I wanted to discuss was there are new directions now that are going on. So how do we think of what happens if you begin to take into account the curvature of the fronts? So if you now revisit the overturning circulation within a front, then it turns out that now the onset of instability happens when a third variable comes in, which is the conservation of angular momentum. And Christian Buckingham, in a series of JPO papers in 2019, showed that the same criteria that I was showing you in the beginning of the talk, 1 plus Rossby number minus 1 over Richardson number, now gets modified by these factors of curvature number. So 1 plus curvature number and 1 plus curvature number squared. The interesting thing is, if I was thinking of a linear front, which is on the left-hand side, then the anticyclones are always almost unstable, even at large Richardson numbers. And the stability boundary is shown here for cyclones and anticyclones on the left-hand side. But now if you begin to introduce curvature, then some very, very interesting and even counterintuitive effects happen. Firstly, you can get, it's not surprising that you get centrifugal instability, but then there are regions now where the flow used to be stable for cyclonic vortices that is now unstable to symmetric instability. So order 1 Rossby number, but Richardson number between 0 and 1, the flow is now much more symmetrically unstable than it was before. A second thing, a very interesting effect that happens is if you go to Richardson number like order 5 or 6, between 4 and 6, then even strong anticyclones can now begin to have become stable. So at low Richardson numbers, the curvature tends to stabilize the anticyclonic flow and destabilize the cyclonic flow. And that's quite counterintuitive. And one of the puzzles was, why do we see so many anticyclones, particularly in the Arctic and other places? And I think the strong curvature effects have something to do with it. There's also work that Mani and his student Suraj have done, Suraj's PhD thesis, which I think relates to some of this work. And we are currently making those connections now that Suraj is here in my lab. So I hope I've shown you that there's a profusion of ongoing work on sub-mesoscale processes. I did not get to talk about the role of topography and role of curvature, but there's certainly a lot going on there. There are a lot of very interesting large-scale observations from space which are planned for SWOT and S-mode. S-mode already has done some pilot studies that, again, multiple international collaborations going on, both for SWOT and S-mode. There are many numerical models that show the profusion of these processes, many studies related to that. And now more and more, the community is thinking about the contribution of such things to weather, to synoptic timescales, as well as to monsoon, as I was talking about, or cyclone, in terms of the aftermath of subduction of these blobs of warm water. The contribution of these sub-mesoscale processes are certainly missing from our global climate models. So how do we think about those? Another topic I didn't talk about was the interaction of these processes with near inertial waves. So, and how the production of near inertial waves, their advection, their dissipation is getting affected by sub-mesoscale processes, and vice versa. There's a feedback between the two. So just to end, I'm going to just remind you of the things that I did not cover in this talk, and they're shown on the right here. And I'm just going to end here with a movie that one of my students made yesterday. And so here we have a series of 3 fronts from the north to the south. And you can see that the northernmost begins to go unstable the fastest. And then the middle one begins to go unstable to the ageostrophic baroclinic instability, and then the last one. And then these fronts begin to interact with each other. And what's shown on the lower left-hand side is the stratification. So the water gets much more stratified as time goes on. And also there is, of course, in this case, we are not forcing it. So we see some inverse cascade. But what's also very interesting is that we see these near inertial waves that are generated by the fronts themselves. They get trapped in the eddies, and you're seeing one signature of that. And as you know, what is shown on the right-hand side is the section where the dashed line is. So as you go through here, these strong up and down welling signatures are around the eddy are related to the near inertial waves. So some very, very interesting dynamics going on. And it turns out that this dynamics also has a strong role to play in terms of ecosystems. So that's also one of the things that we are currently doing. All right, I'll stop here and take questions.
Thanks a lot for this very interesting talk. So if there is questions, it can be on the chat, or you can turn on your microphone.
All right, then I will ask a question if nobody else is asking a question. So let me go to the first slide here. So this is a question for the students. As I showed you, we see that the northernmost front goes unstable first, then the middle front at 0, and then the southernmost front. And so I'll tell you that these are unforced simulations. We just started them from very similar horizontal buoyancy gradients are pretty much identical. So why is it that the northernmost front goes unstable first? So I will take the answers, and you get brownie points. So next time you see me, I'll treat you to a brownie. Any students? Come on, go ahead and guess an answer. All right, I'll give you the answer because I don't want to delay the break. So if you look at the initial condition, I remember I told you that the ageostrophic baroclinic instability has a length scale proportionality where it's proportional to the mixed layer depth edge. So what I did not tell you was the initial mixed layer depth. If you think about it, the way we've set up the horizontal buoyancy gradients, it's deepest in the northernmost part of the domain. So because of that edge squared dependence, the ageostrophic baroclinic instability appears first in the northernmost front, and then in the middle one, and then in the southern one. So that's the answer for why you see the sequence of ageostrophic baroclinic instability, and then it goes unstable, and you see these beautiful features. All right, I'll stop there.
Just then a question: why do you have this mesoscale eddies only at the southern part at the end?
So remember, as I said, because these are unforced simulations, there is this inverse cascade going on, and so the sub-mesoscales themselves do arrange themselves to go to larger scales. So even as the stratification is, even as these isopycnal surfaces are tilting and creating larger stratification, we do have the tendency of the eddies to merge and form these larger scale features. And so that merging goes on much more quickly in the northern portions. You can see some of that happening in the northern portions here already. And then in the southern portion, again, there is a time lag. And so by the time we ended the simulation, we had these mesoscale features in the south. And so I wouldn't analyze this part for the sub-mesoscale part, but it's very interesting. And what's also interesting are these up and downwelling motions at the edges of the eddies that have to do with how the near inertial waves are interacting with the eddies. One of the other things I would like to discuss, in case people here haven't seen it, one of the fascinating things about this simulation is that when we were doing these simulations, maybe even 5 years ago with Amala, they used to take us kind of days to run. And now we are running this in the framework of something called Oceanigans, which we just learned from the Ocean Sciences meeting maybe 2 months ago. And we can run these simulations much faster now in the Oceanigans framework. So again, an advertisement for a different kind of model written in the Julia language. Okay.
So
right.
I think there is no other questions. So thank you for your talk, and we'll have a short break of 15 minutes before the talk by Eric Dassaro.
Sure. I hope I've stopped sharing my screen. Yes.
Yes.
Okay.
So
thank you, Sylvain, and thank you, everyone.
thank you.